Hi guys, today let's try out some exam-style questions related to optical isomers. First of all, let's figure out what are optical isomers and what is optical isomerism. So when we talk about isomer, it means the organic compounds with the same molecular formula but different structures. For example, if I have organic compound that have the molecular formula of C4H9OH, it could be possibly like this, a straight carbon chain with the OH attached in the middle, or it could be like this with the hydroxyl group attached to the end. Or it could possibly have different carbon chain structures as well. But all of this all belong to structural isomers that we learned before. They are different in the way they arrange in a 2D way. However, the optical isomer belong to this group called stereoisomers. Stereo means 3D space. So stereoisomers means they are different in space, spatial-wise. Well, optical isomers are one of it. There is another one of stereoisomers that you learned was the 𝘾𝙉𝙼𝙀 that you learned in the alkene. But we won't go into too much in the details for the 𝘾𝙼 today. So the optical isomerism arises with the necessary condition. Firstly, you will need a carbon in the center, and you will need 4 different groups attached to this carbon in the center. Note that it have to be 4 different groups. If you had 2 or 3 groups that are the same, then they won't have isomerism. So our definition for the optical isomers is that they are chiral, as in they are mirror image to each other, and they are non-superimposable. So this word means no overlap. They will never fully overlap with each other. I know it is very abstract to imagine it. So now let's have a look at this video. So here I made 2 models to show the optical isomer structures. Imagine these 2 black balls are the carbons, while the 4 groups with different colors are the different functional groups or whatever the R groups attached to the central carbon, aka the chiral center. As you can see, they are mirror image to each other. Imagine there's a mirror here in the middle. But then they are non-superimposable, as in no matter how hard you try, they just cannot overlap. For example, now I want the purple one to overlap, like in this case. So red one overlap as well. But then the blue will overlap with the green, and the green will overlap with the blue. So they never fully overlap. I can try. Okay. Hopefully this video can clarify better what are optical isomers. So another question about optical isomer is that why is named optical? What's it to do with optic? Because whenever we talk about optic, it should be something to do with light. What's the isomer to do with light then? Then we need to have a look at a very important physical property of the optical isomers. So usually when we think about the physical properties, you will talk about the boiling point, melting point, hardness, volatility, etc. So for the optical isomers, they should be very similar in these physical properties because they have exactly the same structure and functional groups. However, there's very important characterization techniques to identify two optical isomers is that it will rotate the plane polarized light to different directions. So what does that mean? Plane polarized light. So here is the characterization technique or machine I talked about before, which is called polarimeter. In this polarimeter, we will have a light, a normal light, shining through a polarizing filter. So what's coming out will be a polarized light. And we'll let this light go through our sample. In here, I have my optical isomers. And this sample will rotate the light to a different angle. And you will see it here, and you will clearly see what are the angle that's being rotated. So for two optical isomers, there will be one of it rotates the light to a clockwise direction. So we can call it a plus isomer, and another one will rotate it to anti-clockwise direction. So we can call it a minus isomer. So using this, we will distinguish which type of isomers exist. But sometimes the isomers will mix together with different ratios. So for example, if I have 80% of the plus isomers and 20% of the minus, I'll end up having a net rotation of a positive clockwise rotation because I have more positive one. Oppositely, if I have less positive one, but more negative one, I will end up having a negative or anti-clockwise rotation. So for these type of isomers, as long as they have rotation for the plane polarized light, we can call they are optically active. Okay. However, if by coincidence, we have exactly the same ratio of the two isomers, which is 50-50%, then you will see a net rotation of 0 degree, as in you won't see a rotation, and that's not optically active because the rotation cancels out each other as they are the same ratio. So the knowledge for the optical isomerism can be used on the reaction mechanisms as well. Before, when you learn the nucleophilic substitution mechanism for the haloalkane, you should learn that there are two types of nucleophilic substitution mechanism. One is called SN2 and one is called SN1. In fact, these two mechanisms, they will produce different type of optical isomers. So for example, if you have a look at the SN2 reaction, you will see that because SN2 reaction is a one-off reaction, so the nucleophile will attack from the back. They will always attack from the back because you got a stereo hindrance here. This is a pretty big atom. So all of your product will be inversed at the end. And you will end up having a optically active mixture that will rotate the light. Okay. However, for the SN1 reaction, if we have a look at the mechanism here, we know that SN1 reaction is a two-step reaction where you will have your haloalkane coming out first, and then you will have a planar shaped intermediate with a carbocation in the middle, and your nucleophile attack this carbocation. So if this intermediate is a planar, then you will attack it from either side. If you look at this image, imagine this is the 2D planar here, and the nucleophile could be attacked from either side. So you got a 50-50 chance to get a plus isomer and a minus one. So if you get exactly the same ratio and they will not rotate the plane polarized light, and we call this mixture, which is 50-50%, that does not rotate the light, a racemic mixture. All right. Now let's try out some real exam questions that was coming out on from the previous past paper. So here, 2-bromobutane can react with the cyanide, which is nucleophile, and this nucleophilic substitution. Suggest with the reason whether a reaction follows a SN1 or SN2 mechanism if only one stereoisomer was obtained as a product. So we just mentioned if they are SN1 mechanism, it will have a racemic mixture and it will be 50-50%. But for SN2 mechanism, because it always attack from the back, so you will end up only having one stereoisomer. So therefore, the answer for this is the SN2 mechanism, because the SN1 will form a racemic mixture. Okay. And the next is state an instrument that could be used to determine whether the product with a single enantiomer or racemic mixture. So remember, the only way to distinguish the stereoisomers is the polarimeter. If there is a single enantiomer in the sample, only one, or a different ratio, you will see a rotation. However, if it's a racemic mixture, then you won't see rotation. And that's the application of the knowledge for stereoisomers and the reaction mechanism.